Up until now, we've used solely our intuition to compute limits. However, to move forward, it is necessary to speak about the precise definition of a limit. In this video, we will talk about how we mathematically define a limit, and then we will use this definition to prove that the limits we've computed up until now are correct. Previously, we guessed the limits of these two sequences. For the sequence on the left, we said that the limit does not exist, or is infinity because n just gets larger and larger. For the sequence on the right, we said that the limit is 0, because as we increase n, the value of 1 over n seems to get closer and closer to 0. But these answers are at best just guesses. We cannot test for every possible number. And so, mathematicians have crafted a tool to test our guesses. And the tool is the precise definition of the limit. But let me emphasize that the definition of a limit cannot be used to compute the limit. It can only be used to prove that our guess is right. And so to find the limit, we first need to have a guess. And then we prove that guess. Sometimes we can use the definition to help us make a guess. And then, when we have that guess, we again use the definition to verify that our guess is correct. Let us look at this example again, and let us try to develop an intuitive criterion to verify that our guess for the limit is correct. Here I have redrawn the plot so that each tick is 100 times greater than the previous one. So here I have 100 and the previous one is 1, and the next one is 100 times greater. That's 10,000, and the same is true for the vertical axis. And I did this so that we can easily see how these values here that are very close to 0 are changing. Now, we recall that our guess for the limit is 0, so this is our guess, and we're going to show that our guess is correct. So, we will develop that criterion. First, let's think of a number, n, in this case, 100. And so we can also think of the term where n is 100, so that's around 0.01 or 1 over 100. Now, the difference between that term and our guess, which is 0, is this arrow, the black arrow. And if we go and find another number greater than 100, for example, this number here, this arrow becomes a little bit smaller. And for a limit to be the real limit, these arrows must become increasingly smaller and smaller. And that means that the difference between any term of the sequence and our guess must continuously get smaller and smaller. I think that makes sense as a definition of the limit. So again, we think of a number, n. We look at the difference between the guess, which is 0 in this case, and a sub n. Then we look at all the numbers to the right of a sub n. That means we look at all the terms for integers greater than 100 here. And so when we look at them, their distance from our guess must get smaller and smaller and smaller. And that is what I think is a sensible definition of the limit. So again, to check if our guess, in this case 0, is the limit, first we think of that term. In this case, 100, a sub 100. And then we ask the question, are the next terms, meaning the terms after a sub 100, that is like a sub 101, a sub 1000, and so on, are they getting closer and closer to our guess? And if yes, if they are getting closer and closer, like this one, then our guess must be the correct limit. And if they don't get closer and closer, then let's find another a. Let's find another term in a and repeat this b. If, however, we try, we cannot find a term in a, then probably our guess is wrong. So our guess can only be right if the distance between our guess and succeeding values or terms of the sequence get smaller and smaller, meaning the arrow gets shorter and shorter. Now here, we will try to have another guess and see if it is correct or wrong. So previously our guess is that the limit of this sequence is 0. Here, we will try with a guess that is 1 over 100,000. So that means we have an n of 100,000 here. So suppose this is our guess. Is this a correct limit? So using the steps we have developed previously, first we guess the limit, and this is our guess, 1 over 100,000. Then we call that L, so that we can have any guess, and then let's just call that guess L. Now we think of a term, a sub m sub epsilon, that is very close to our guess. So this is our guess. We choose a term near it. In actuality, you can choose any term, even if it's far, but it makes it easier if we choose the term that is close to the guess. In this example, let's use this term here, which is between 0.00001 and 0.001. Let's use this term that is for n equals 10,000. Let's give it a name. Let's call this term a sub m sub epsilon, and let's call this 10,000 our m sub epsilon. And let's call this distance, this length of the arrow, let's call that epsilon. So you see that the distance here is dependent on the term that we chose. And so that's why we put a sub epsilon for our m. So this is our m sub epsilon, 10,000, and at that m sub epsilon, this is the distance. This is the arrow that we have. This is the epsilon that we have. And the next question is, are the next terms, are the terms after m sub epsilon, in this case after 10,000, do they get closer and closer to L, which is our initial guess? What that means is that we have to show that for all these k greater than our m sub epsilon, so this is our m sub epsilon here, and we have to show that for all k that is greater than that m sub epsilon, which is 10,000, we have to show that all the a sub k's must get closer and closer to our guess, which is, this is our guess, 1 over 100,000. So all of these terms after m sub epsilon is our a sub k. And so let us check if it does get closer and closer, which means should it get smaller and smaller, shorter and shorter than our chosen epsilon here. So if we choose this point, it's around epsilon, maybe that's fine. The problem is the next point. This is another a sub k because this is after this 10,000 here, after our a sub m sub epsilon. So this is an a sub k. The problem is that this arrow is clearly longer than the chosen epsilon. So we have a problem. This means either that our guess is wrong or that we have to choose another m sub epsilon. And you will see that for this problem, if you try, you can never find an m sub epsilon that doesn't become like this. Any m sub epsilon that you choose, you can choose 10,000, a million, a billion, you will see that whatever you choose, your a sub k, you will always have an a sub k where the arrow becomes greater than your epsilon. And so what that means for us is that our limit, our guess for the limit is wrong. And so this is a wrong limit. 1 over 100,000 is not the limit of this sequence. And if we make that more precise, mathematicians state it this way. We say that L is the limit of the sequence a sub n if and only if for any small difference epsilon, which is a positive number because it's the distance there exists an integer m sub epsilon, in this case 10,000, such that for all integers to the right of that m sub epsilon, then the distance between our guess and a sub k must be less than our epsilon. So if we can find this m sub epsilon, then probably our guess is correct. So mathematicians write it this way in a more concise manner. So this is the meaning of this expression is such that for all epsilon greater than 0, there exists an integer or a natural number m sub epsilon such that for all k greater than m sub epsilon, that means to the right of m sub epsilon, this expression holds. This expression means the distance between our guess and all succeeding terms must be less than our epsilon. So the goal of this, if you want to show that L is our limit, we have to find this m sub epsilon. We have to find this m sub epsilon such that all the terms after m sub epsilon will satisfy this inequality here. Finally, we will now be using the precise definition of the limit of a sequence to show that the limit of this sequence is indeed 0. So here I just wrote again the precise definition, and we will go over the steps. First is to guess the limit. Here we are guessing that the limit is 0, and we're going to try to show that this guess is correct. The goal is to actually find an m sub epsilon for any given epsilon. If we can find that m sub epsilon, then we have shown that our limit is correct. If we cannot find that m sub epsilon, then our limit is wrong. Usually we start by stating the necessary condition. That is this condition here, which is the distance between our guess, L, and the succeeding terms, a sub k, where k must be greater than m sub epsilon. This distance must be smaller than our epsilon. So that's the necessary condition. And then we just try to simplify that. So first we replace L with our guess, which is 0. We replace a sub k with our term here, 1 over k, and that's less than epsilon. And then we do a bit of manipulation, and we obtain this. What this means is that this expression here is equivalent to this. So we can actually replace this with this. And so our statement now becomes like this. For all epsilon greater than 0, there exists an m sub epsilon such that all k greater than that number, k must be greater than 1 over epsilon. And this is a very nice expression, because what this is telling us is that for all k that is greater than this number, k will be greater than this number. Again, for all k greater than this number, k is greater than this number, which means we only have to equate this number m sub epsilon and 1 over epsilon. And if we do that, this statement always holds true, because if we choose m sub epsilon as 1 over epsilon, then the statement will read like, for all k greater than 1 over epsilon, k is greater than 1 over epsilon. And that's just true because it's just a repetition. K greater than 1 over epsilon is greater than k, is implying k greater than 1 over epsilon. That's just a repetition. That's a tautology. And so it's a true statement. And therefore, we have found our m sub epsilon. That means we just have to equate it with 1 over epsilon. And because we are able to find this m sub epsilon, then our guess is correct. In fact, the limit of this sequence is 0 because we are able to find this necessary m sub epsilon. Now we will apply the precise definition of the limit to the sequence n and see what happens as n gets closer to infinity or approaches infinity. So here I just wrote the definition again. The first step is to guess a limit. In this case, we really don't have a guess, but we will assume that there is some number L that is the limit of this sequence. So let's assume that that number exists. We don't know if it does exist, but suppose it exists. And then we recall the goal. We have to find the m sub epsilon here for any given epsilon. If we can find this m sub epsilon, then in fact L is the limit that we're looking for. There exists an L that satisfies these conditions. Then we just state the necessary condition. Again, that is just the distance between the limit, which is L, and the term a sub k after m sub epsilon must be less than epsilon. So the distance here must be less than epsilon. Then we try to manipulate that. We just first replace our guess. Our guess is just L because we don't really know. And then our a sub k is k because this is our sequence. It's just n. So we replace it with k, and that should be less than epsilon. Now we can just switch those terms, because this is an absolute value symbol, so that's the same as k minus L is less than epsilon. And we do this so that we can do the following. We can add L to both sides so this expression here becomes this expression. But we know that this expression, if we put the absolute value symbol outside, we can say that this is smaller than this one. So we can establish that. And so we can get rid of this middle expression. And we can just have L plus k minus L, which is just k is less than L plus epsilon. And there's a problem there, because our expression here now becomes for all k greater than m sub epsilon, k is smaller than the limit. Let's say that again. K is smaller than the limit. But why is that a problem? That's a problem because we have to show that for all k bigger than m sub epsilon, meaning there is no bounds for our k can get bigger and bigger for all of those k, because all of those k is referring to all of those k. And yet this says that for all of those k's, they will be smaller than the limit if we have the limit. And you see that that cannot happen because we have just said that a just gets bigger and bigger. And so if we have a fixed limit, suppose the limit is L, k can always be greater than L, right? And so this is a contradiction. You cannot have k being boundless and at the same time being smaller than some number. So k can always be made bigger than any number. And so we cannot find any m sub epsilon there, because for any m sub epsilon we choose, if the limit is L, it says that k will be less than L plus epsilon, and that's just not going to be true, right? And so these two statements cannot coexist, and that means that L does not exist in the first place, because this is the only part where we made an assumption that is probably incorrect. All the other steps we took were valid manipulations, and only this assumption is questionable. And so, because we had a contradiction here, by proof of contradiction, we have shown that this cannot be the case. L cannot have existed. L cannot exist. And that is how we show that the limit of n as n approaches infinity does not exist, because we cannot find the m sub epsilon that we need. Here we will show that the limit of this alternating sequence of negative 1s and 1s does not exist, because this sequence only alternates between negative 1 and 1 depending on whether n is odd or even. And we will use the precise definition of the limit of a sequence to show that such limit does not exist. First, let's have a guess. And we don't really know what to guess, but let's just assume that that number exists. Let's call that L. And then the goal is to find this m sub epsilon here for any given epsilon. So we must be able to choose any epsilon, and we must be able to find an m sub epsilon if we are given any of these epsilons. And then the necessary condition is that the distance between the limit L, which is our guess, and a sub k, which is the kth term, and k is greater than this epsilon, m sub epsilon, this distance must be smaller than our epsilon here. Then let's do some manipulation. Here we just substitute. Our guess is still L, and then our kth term is minus 1 raised to the k, and that should be less than epsilon. And what that means is that these two inequalities must be true. L minus negative 1 must be less than epsilon, and L minus positive 1 must be less than epsilon. That's because k here alternates between odd and even for any value of k greater than m sub epsilon. You will always have odd and even values of k. And so for odd values of k, this must be true. And for even values of k, this must be true. And so both must be true, because we will always have even and odd values of k for k greater than m sub epsilon. Now, if these statements are true, both of them are true, then we can, so let's keep this statement as is, and this one we can just switch the terms, because this is inside the absolute value symbol. This is just distance, so we can choose whichever one comes first. But by putting it this way, we can do the following addition. So we add the left terms. This is the left term here, this is the left term here. We add them together, and we add the right terms. This is the right term here, this is the right term here. And so we have epsilon plus epsilon, and here we have this. And why do we want to do that? Is because this sum is greater than when you put the absolute value symbol outside. So if you just remove all the absolute value symbols here and just put it outside, we've done this in the previous slide, and we call that the triangle inequality, then we can just do the addition. Minus 1 minus L plus L minus 1. And so the L's cancel, and we're left with the absolute value of negative 2, and that is just 2. And on the right side, we have 2 times epsilon. And that means that epsilon must be greater than 1. I just transferred the epsilon to the other side, and so that reverses this. It means this condition implies that epsilon must be greater than 1. But we have a problem if that's the case, because we require that this must be true for all epsilon greater than 0, not only for epsilon greater than 1. So what if we choose epsilon equals 0.5? Then this will not be satisfied. And so that's a contradiction, because the requirement is that we must be able to choose whatever epsilon we have, and yet this statement, if the limit is L, if it exists, it necessarily means that epsilon must be greater than 1. And that is where the problem is. It's a contradiction. Again, because we can choose any epsilon, it could be smaller than 1, and yet this statement says that it should be greater than 1. So it does not satisfy the definition. And so we cannot find that m sub epsilon, because we can't even go to this statement. This statement is not satisfied anymore. The very first part of the statement is not satisfied, because this statement here only means that epsilon must be greater than 1. Meaning, if we choose an epsilon that is less than 1, this will not be true anymore. And so it's not true for all epsilon. There's some epsilon where it's not true. And so we cannot find L, or we say L does not exist, because the definition must still work for E, which is less than or equal to 1, for epsilon less than or equal to 1. And yet, that's not what we see here. So it's a proof by contradiction. This statement contradicts our requirement here. And that means that we made a wrong assumption somewhere, and because all of the manipulations we did in steps 2, 3, and 4 are all valid, or in step 4 are all valid, then our mistake must be in this assumption that there exists a limit L. In this video, we have discussed what I think is one of the most challenging concepts in calculus, and that is the precise definition of a limit. And that definition is written here. That is that the limit is L if and only if, for any small difference epsilon, there exists an integer or a natural number m sub epsilon, such that for all integers to the right of that m sub epsilon, the difference between the limit and the terms after m sub epsilon, that difference must be smaller than epsilon. And we write it more concisely in the manner in the right. And again, this definition is very hard to use to find or to compute the limit. So we don't really use this to compute the limits. We use this to prove that the limit that we have guessed or found is correct. So the steps would be to first guess the limit and then use this definition to prove that our guess is correct. And using those steps, we have shown that in fact the limit of 1 over n is indeed 0, but we had to guess first that it is 0 and then apply the definition. We also did the same for the limit of the sequence n, and also for the alternating sequence -1 raised to the n. And we have shown that for both of these sequences, the limit does not exist because it produces a contradiction in the definition. And so it does not satisfy the definition of the limit. In the next video, we will be computing more limits by guessing and using the arithmetic operations on limits.